Hi, this is Shane Somerville, and this is Chapter 6, VLANs of CCNA2 version 6. There are several sections to this chapter, it's a little longer than the previous chapters. So we get into Section 1 on VLAN segmentation, and I'll stop the video there and create another video for VLAN implementation, where we actually get into VLAN port assignments and configuring trunks, and troubleshooting VLAN configurations. And then we get into inter-VLAN routing using routers. So legacy inter-VLAN routing using multiple routers or multiple ports on a router and router on a stick. These are the two options that are discussed in this chapter. There's also multi-layer switching, where you use a multi-layer switch to route between VLANs. There's three options, one being legacy with a router with multiple ports. Router on a stick uses sub-interfaces on a traditional router. And the third option, a multi-layer switch, which looks like a switch, but it's capable of layer 3 routing. So VLAN segmentation. So a VLAN allows you to have virtual local area networks on a switch. So normally an entire switch, each port on the switch, when we plug these in, you would be in one broadcast domain, so all of these switches would be in the same one large broadcast domain because they're all plugged into the same router port. Right? So this would be one subnet. That's the traditional method. Right? But what a VLAN allows you to do is to segment the network down and have each port assigned to a different VLAN. So you could have this port plugged into a PC, it's on VLAN 2. Then you could take another port on the switch, plug that into a PC and have that on VLAN 3, and so on. So each port gets assigned to a VLAN. By default, they're all on VLAN 1. But you can change that, so each port could be on a different VLAN. Okay, so it allows for segmentation. Each of these VLANs, if you're on a different VLAN, these two ports cannot communicate directly over the switch. They have to be routed. So to communicate between VLANs requires a router. VLANs are layer 2. They're all layer 2. So if you're on a VLAN, it's all layer 2. If you want to communicate between VLANs, requires a router. Okay, so in that way, if you require a router, that means each VLAN is a separate broadcast domain. And it's a separate subnet. And the router routes between those subnets. So, some VLAN definitions. Allows for segmenting the network based on factors such as function, project team, or application without regard of the physical location of the device. Okay, so throughout your entire switch network, you could decide to place a device on a specific VLAN and segment it from other devices that might be in the same room. They would have to pass through the router. And because they have to pass through the router, it allows you to implement security policies. So VLANs enable implementation of access and security policies, so access control lists between those VLANs. It is a logical partition of the layer 2 network, so the entire VLAN and the trunks that connect those ports on different switches are all layer 2. Multiple partitions can be created, allowing multiple VLANs to coexist. So you can have multiple VLANs on a switch, and then you assign the ports to a specific VLAN. Each VLAN is a broadcast domain, usually with its own IP network, so its own network or subnetwork. VLANs are mutually isolated, and packets only pass between them via a router, so you require a router to route between VLANs. Partitioning of a layer 2 network takes place inside a layer 2 device, usually a switch. Yes, so it's a switch, and then you assign VLANs or ports to VLANs. Hosts grouped within a VLAN are unaware of the VLAN's existence. All right, so it's completely a switch configuration. Yeah. So there's no additional software or anything required on the end devices. some of the benefits. So it improves security, reduce cost because you can use one physical network. You have better performance because you have smaller broadcast domains. It can be more efficient if it's configured properly. And a simpler project and application management. Maybe. And again, proper configuration and understanding of how VLANs work are important to make that actually turn out to be true. So in this diagram it shows you have color-coded VLANs. So VLAN 30, and you notice the IP here, 172.17.30/24, 172.17.30, again with the unique IP but in the same subnet, right? But whereas these are different subnets. So VLAN 30, VLAN 20, they're in different subnets, but you can have them all plugged into the switch and keeps them separated. Now you could always do this. You could always plug in multiple PCs to a switch and assign them to different subnets, and they would have to go to the router to communicate. But if you were to do that without a VLAN, then you would still all be in one broadcast domain. You'd be receiving traffic from all of those different subnets, layer 2, right? So when an unknown frame with an unknown destination, so you need to build the frame, the ARP broadcast goes out, it would still be received by all devices. But VLANs segment the broadcast domains, so in that way, any broadcasts that leave VLAN 10 from this device would pass into this port, but they would not go into these other devices. They would traverse this trunk. Trunks are between switches, and they would go to this other device on VLAN 10. Not pass out these ports, and the broadcast would also go up to the router. The router does not forward broadcasts. So the broadcast domain is as large as your VLAN is extended throughout your switch network. The enterprise composite network model actually doesn't recommend separating your VLANs in this way. It becomes difficult to troubleshoot if you have it based on the team or the department for your VLANs. It's actually better if you assign all ports on a switch to one VLAN or a switch block. So a stack of switches in a wiring closet in an area of your network should actually be all ports in one VLAN if you can. And that way you can compartmentalize issues within a VLAN. Okay, but you can do it this way. You can have multiple departments and have your VLAN spread across your network. But if there becomes issues, it can be more difficult to troubleshoot as your VLAN and your broadcast domain are spread throughout your network. Okay, so there's a couple of design ideas and things to consider when setting up your VLANs. There are different types of VLANs. So data VLAN with user-generated traffic, this would be predominantly used, right? So you have devices and PCs and everything connected to a data VLAN. You have the default VLAN. Okay, this is all switch ports become part of the VLAN until the switch is configured. So this is VLAN 1. If you do a show VLAN, you'd see that all ports are part of VLAN 1 by default. This term, the native VLAN, is specific, and there are configurations related to the native VLAN. Okay, so the native VLAN is used for untagged traffic. We haven't discussed what tagged or untagged traffic is yet, but the concept is if you have a port with VLAN, and say this is on VLAN 10, you have a device, and it enters the switch, and it has to traverse a link to get to another switch, and it also might have devices on VLAN 10, let's say. This trunk, the whole purpose of a trunk is to carry traffic for multiple VLANs. The only way they can differentiate between traffic from one VLAN to another is to mark it in some way. So as soon as this frame enters here, the switch will not allow it to pass out, or it cannot be passed out any of these other VLANs. So let's say this is VLAN 20. The only way it could get to VLAN 20 is if it was routed into that other subnet. Okay, so when the frame is sent on a trunk link, it can actually be tagged, and that's 802.1q. There's also something called ISL, which it encapsulates. So you can either encapsulate the frame with an ISL frame, send it along the trunk, or you can use 802.1q to insert a tag into the frame to mark it for a specific VLAN. And that is respected on the other switch. So when it receives it, it can see that marking is for VLAN 10, and it allows the frame to exit for a specific VLAN. That is tagged traffic. Then you have the native VLAN is a specific VLAN that allows untagged traffic. So if you have a device that's sending a frame across a trunk link, but it doesn't have any tagging on it, then it will pass through the native VLAN. Okay, so 802.1q has a mechanism for untagged traffic. ISL does not. Everything has to be encapsulated. And then there's the management VLAN. Management VLAN is used for management. So the VLAN that you use to connect to the device via SSH or Telnet, right? That's the management VLAN, or HTTP or HTTPS. So you want to have a VLAN in your network that is used for management, and you have to have controlled access to that VLAN, and it's a security mechanism. You don't want the potential that any user device that's connected to, say, VLAN 10 is a data VLAN, and users and accounting are connected. There's no reason why any of those devices should be able to administer the switch. All right, so you don't want to leave it to your SSH passwords and the user passwords. You can also take an extra level of precaution and have a management VLAN that has controlled access. Okay, and that's the purpose of a management VLAN. There's nothing particularly special about it other than it has control. The ports are only in secured areas that have access to the management VLAN. Okay, so you configure VLANs. They can be data VLANs. A data VLAN that you use for management is termed a management VLAN, but it's just a data VLAN. This native VLAN actually has a configuration related to it, marking it as a native VLAN, and that's used for untagged traffic. So this is show VLAN brief, and you can see there's the VLAN number, VLAN 1. It's the default VLAN. You can't rename it. You can't delete it. These are also default VLANs, and you just leave those alone. So you would create other VLANs in this series of numbers between here and then after again. And you can see that all of the ports are part of VLAN 1 by default, so they can all talk to each other, right, including the gigabit ports. So all VLANs part of VLAN 1 by default. Native VLAN is also VLAN 1 by default. It allows untagged traffic. And the management VLAN, because you're likely to connect to the SSH IP address for VLAN 1, right? And you also have this concept of voice VLANs. So a voice VLAN carries voice traffic. Now, a voice VLAN is a particular, it's a special command in the Cisco device, and it creates an access port that allows tag traffic for voice. So let's start up here. Switch port configured to support voice traffic. Port sends CDP, Cisco Discovery Protocol frames to provide information used on the IP phone. So you have CDP frames to discover what this device is. And you might have PoE, and the switch would, or the phone would have to actually communicate with the switch to communicate what the requirements are for power, because there are different power settings on a PoE port on a switch. And in this one, it says port forwards frames associated with VLAN 150. So this is an access port, but it's a special configuration because it says it uses 150 for the voice VLAN and prioritizes voice traffic. So this device, this VoIP phone, has a switch in it, allows you to connect here. Although this is an access port, you can actually have this phone on VLAN 150, right? So VLAN 150 with prioritization of VoIP packets, and a PC on VLAN 20 connected to the switch, which segments this traffic. The VoIP traffic's in a separate VLAN than the data VLAN. And to communicate between these two devices directly, you would have to pass through the router. Now this link between the two switches, this is a trunk, and this would also be a trunk. And since you only have one port on the router in use, this is called a router on a stick. And it uses what's called sub-interfaces. You would have a sub-interface for the 150 VLAN and another sub-interface for the 20 VLAN, each with a different IP, and allowed this one router with one port to route between these two VLANs. So voice VLANs. VoIP traffic is time sensitive. It needs less than 150 milliseconds across the network. So it needs consistent, assured bandwidth for voice quality. Okay, it uses UDP to send VoIP packets. They don't resend. It wouldn't make any sense for voice to resend frames. It is time sensitive. So unless you don't have this less than 150 milliseconds of delay across the network, then you're going to have noticeable jitter in your voice conversation. So to prevent that, so if there's bursty traffic on your data network, right, and all of a sudden the frames from VoIP are getting dropped, you'll get jitter. So you want to prioritize the VoIP traffic. So transmission priority over other types of traffic. This is term quality of service. And ability to be routed across around congested areas of the network. So again, that's quality of service. Delay of less than 150 milliseconds, and the voice VLAN feature enables access ports to carry IP voice traffic from an IP phone. So it's still an access port, but has two different VLANs, one for VoIP, one for data. This is the only time you can have an access port on two different VLANs. In every other instance, a port belongs to a VLAN. There's a one-to-one relationship. So VLANs in a multi-switched environment. So this shows multiple VLANs, 10, 20, and 30, and then a management VLAN and native VLAN. You also have multiple ports and different VLANs. And it says the links between switches S1, S2, so S1 and S2, and S1, S3 are configured to transmit traffic coming from VLANs 10, 20, 30, and 99 across the network. The network could not function without VLAN trunks. Okay, so these are the trunk links. These switch-to-switch links are trunks. You configure them as trunks, and in previous labs there's a command switch port mode, and then you have the option to configure it as a trunk port. So these links here would have that command configured, switch port mode trunk. Any of these links to a end device, you would configure a switch port and then set the mode as access, so they cannot trunk. And again, trunks carry traffic from multiple VLANs. If these were not trunks, then there would be no marking for the VLAN. So more on VLAN trunks. It says first bullet here, a VLAN trunk is capable of point-to-point link that carries more than one VLAN. So it carries traffic from multiple VLANs. Usually established between switches, so same VLAN devices can communicate even if physically connected to different switches. So it allows your VLAN to be across your entire switch network. And it says usually established between switches because you could have a server connected to a switch via a trunk. So maybe you have a switch, you have a server. This could also be a trunk to the server. And that would allow you to have sub-interfaces on the server, and you could have a sub-interface on VLAN 10 and a sub-interface on VLAN 20 and a sub-interface on VLAN 30, let's say. And then you could have multiple devices all on those different VLANs. And each of these devices could have direct communication to the server without having to pass through a router. So by having a trunk here, it would allow traffic from VLAN 10 to pass directly through the switch and stay on the layer 2 network, right? So stay at that level. without having to be routed and have direct communication to the server, which makes it faster. If you have to go to the router to route between VLANs, then it's going to increase the delay with the communication to the server. So it's a matter of efficiency. Third bullet, a VLAN trunk is not associated with any VLANs. Neither is the trunk port used to establish a trunk link. So it's not on a specific VLAN, it carries traffic for all VLANs between switches or two-way server. Cisco iOS supports 802.1q, a popular VLAN trunking protocol. So you need to know 802.1q is a frame tagging method for trunk links. Frame tagging for trunks. Controlling broadcast domains with VLANs. So again, you have different VLANs. There's faculty, student, and guest. If a broadcast was to leave the faculty VLAN, it would enter this port. It would not. Oh, okay, so this is no VLAN segmentation. So you didn't notice that all of these are on the same subnet to just now. So since these are on the same subnet, if a broadcast enters the switch port, it would be forwarded out every other port other than the one it was received on. Okay, so there's no stopping the broadcast until it reaches the router. Now with VLAN segmentation, you'll notice that these are on different VLANs, different subnets. Okay. So you have a broadcast on VLAN 10, enters the switch. This is VLAN 20, so it doesn't go out this port. This would be a trunk. Trunk would continue to, as a layer 2, trunk would continue to forward the broadcast. It would continue out any port that's on VLAN 10, but would not be able to enter VLAN 20. Okay, so it's a way to break up your broadcast domains into multiple VLANs without requiring additional physical runs. This is one physical network where you actually have one physical cable between these devices, right? But you still have segmentation of your broadcast domains by VLAN. So VLANs can be used to limit the reach of broadcast frames, right? So you're breaking up your layer 2 network into smaller broadcast domains. A VLAN is a broadcast domain of its own. Broadcast frame sent by a device in a specific VLAN is forwarded within that VLAN only. VLANs help control the reach of broadcast frames and their impact in the network. Right? You don't want one large broadcast domain with all of your devices on it. It creates too many broadcasts, too much traffic being used just for broadcasts. Unicast and multicast frames are forwarded within their originating VLAN. You still need to route to enter another VLAN. Tagging of Ethernet frames for identification. So frame tagging, this term frame tagging, is an 802.1q mechanism. It's a process of adding a VLAN identification to the header of the frame. It's used to properly transmit multiple VLANs within a trunk. Okay, so it's at the trunk link. And at this point it's tagged. The tagged frame traverses the trunk link, and that tag is checked on the receiving end, and the frame is forwarded out any VLANs that are on that same, or it's in the same VLAN as the tag. Switches tag frames to identify the VLAN to which it belongs. Different tagging protocols exist. .1q is a very popular example. And again, there was one other one, ISL, or inner switch link, that doesn't perform tagging, and it actually encapsulates the frame. .1q is the protocol you want to learn. And the reason being is that it supports an untagged native VLAN, and that's used for VoIP. Protocol defines the structure of the tagging header of the frame, switches add VLAN tags to the frames before placing them into trunk links, and removes the tags before forwarding the frames through non-trunk ports. So the tag is examined and removed at this point When the frame exits VLAN 10, there's no tagging required anymore. Okay, so it's just for this trunk link. When properly tagged, the frames can traverse any number of switches via trunk links and still be forwarded to the correct VLAN. So here it shows tagging of an Ethernet frame. This is your frame here. And inside this data, this is your packet. It's encapsulated inside of a frame. And you can see after the source MAC address, there is a tag area here. And if you were to examine that, you have 2 bytes for the type, 3 bits for priority CFI, and the VLAN ID is 12 bits. Okay, so that's 12 binary bits and all the different combinations that you might have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So you have 12 bits to change from VLAN 1 to however number of combinations you can have with 12 bits. Native VLANs and .1Q tagging. So controlled traffic sent on the native VLAN should not be tagged. Frames received untagged. Frames received untagged remain untagged and are placed in the native VLAN. If there are no ports associated with the native VLAN, then no other trunk links on an untagged frame is dropped. So you have to have a port on the native VLAN. You have to have a trunk. There's going to be a native VLAN on the trunk with .1Q. And then you should have a port on that native VLAN if you wanted to forward untagged traffic. When configuring a switch port on a Cisco switch, configure devices so they do not send tagged frames on the native VLAN. Okay, so there'd be a configuration for that. They're saying don't do it. In Cisco switches, the native VLAN is VLAN 1 by default, and you should change it to be something else other than native or VLAN 1. So here's voice VLAN tagging again. So you have a port on a switch, port 18, and that's plugged into this whole thing represents a Cisco phone. Okay, so this is the 3-port switch on the bottom of this phone. Okay, so it says instructs the phone to tag voice frames with VLAN 150, prioritizes voice frames, and forwards the data frame on VLAN 20. So here we go, port 18, switch port's enabled. It is static access, so it's still an access port, but it has trunk encapsulation of .1Q. The access mode VLAN is 20, native VLAN is still 1, and the voice VLAN of 150. They haven't shown the configuration for how this was set up, but this is a specific configuration for a VoIP phone. There's an activity for packet tracer, just to look at how broadcasts are sent. And again, if the broadcast is sent on VLAN 10, it's received on VLAN 10, not on the other VLANs. But it will traverse the trunk links. Okay, so that's the end of the first section, 6.1, for an introduction to VLANs. And I will create another video for 6.2. Thanks for watching.